Hello, Lakshmi, can you hear me?
Yeah, yes.
Okay, yeah, there was some problem. Okay. Can you see my screen now?
Yeah, yes.
Okay, yeah. So we were discussing question number 5 now. Basically, so you have this kind of configuration, and they have told us to find out what would be the Thevenin equivalent zero sequence impedance of this, right? So we have to draw the zero sequence impedance diagram. Now, so this is 0.35 and this is 0.05, which I've clearly mentioned here. And you have a star connection with solid grounding. So this point is grounded, shorted. And you have this delta connection on the this side, right hand side. So you have this open, and this point is shorted with the ground, right? And this is the transmission line 0.09 per unit. Again, this is starred with uh, no grounding, right? So this, hence this point is open, and again this is 0.35, right? So this shorting is now replaced by this would be resistance, not impedance. This is a mistake that I made. So, and this you have a point P. So clearly you see that this is an open circuit, right? This point is open, again this point is, I mean, any point open, you have an open circuit network. So as a result, you have a, zero sequence impedance would be infinite. So mm, that is what I was actually trying to tell you, that you have to design in your system in such a way that you get the impedance as high as possible, so as to reduce the fault current. So that is why, choosing the correct configuration of the transformers in this type of power system network is very important.
Okay.
Yeah, I hope you understood this. How?
Yeah, yes, yes. Now it's clear. Yes.
Yeah. Okay. Now let us go to, next problems are numerical problems only. Question number 6. So a 20 MVA 6.6 kV three-phase alternator is connected to a three-phase transmission line. The per unit positive, negative, and zero sequence impedances of the alternator are these, right? J.012 and J0.05. Now the neutral of the alternator is connected to ground through a pure resistor, okay, of 0.05. Again, this is a mistake that I have done. So this would be resistance and not impedance in the diagram. And again, the per unit positive, negative, all these sequence impedance of the transmission line, this thing are also mentioned, 0.15 and 0.375 per unit. So a solid ground fault occurs at one phase of the far end of the transmission line. So clearly this statement tells you that this is a line to ground fault, right? Because the fault is occurring at only one phase. So if would have been a occurring at two phase, this would have been double LG fault. So this is a LG fault occurring at the far end of the transmission line. So they are telling ki find out the voltage of the alternator neutral with respect to ground during the fault. So I mean, for your for the convenience, I have drawn this diagram, and I have also mentioned these things, and I have also mentioned the base of the system. Okay. So now we have to find out what is the zero sequence positive, negative, and zero sequence impedances, right? And I mean, this is easy, right? Because you don't have any transformer, so this is straight away addition problem. So you add, and since this is a series network, because the fault is not occurring at this point, otherwise this would have been, this would have been a kind of parallel network, then finding out the impedance would have been different. So just add up your Z1 would be what, 0.12 here and 0.15 here, so 0.27. This is also equal to the negative sequence impedance, and your zero sequence would be 0.05, and your this thing, right, 0.375, so j 0.425. Now you replace everything in this formula, and you also have to add, so don't forget this. So we have a pure resistance grounding, so 0.05, so basically 3 times of that, so 3 into 0.05. So when you do this, you get 3.071 at an angle of minus 8.83 degrees per unit. So your positive, negative and zero sequence current would be one third of this, so this comes out to be 1.0235. So now they have asked us what would be the magnitude of the voltage, of the alternator neutral with respect to ground, right? Neutral with respect to ground. So we require the this zero sequence current, and this is multiplied with the grounded the this thing, right? Your 0.05, which is the all neutral to ground resistance, so 3 times of that. So basically this current into your ground to neutral resistance, so 3 into 0.05, so you get it as 0.153, and you know the what is the base voltage, right, which was 6.6 kV. So you divided by root 3, you get around 585 volt, which is your option number B. So this was straightforward problem. I hope this was clear.
Yes.
Now let's go to question number 7. So 7 and 8 are connected questions. So here a 20 MVA 11 kV alternator with solidly grounded neutral has a subtransient reactance of 0.35 per unit. Now the negative, so this is your positive sequence reactance, because subtransient reactance basically refers to that only. Now the negative and zero sequence reactance are also given here. All the per unit values, okay, fine. A single line to ground fault occurs at the terminals of phase A of the unloaded alternator, right? So this is again a line to ground fault, and somewhere they have mentioned solidly grounded neutral. Yeah, solidly grounded. Therefore, you have no ground to neutral reactance or resistance. So that is why your Xn is 0. Again, you use the same formula, you find this, so your fault current comes out to be 4.412 per unit in terms of line to ground fault. So here you find out the base current, and you find out that your fault current in kiloampere is 4.63, which is your option number E. uh, okay, so now let's go to the connected problem. So here everything is same. A single line to ground fault occurs at the terminals of phase of the unloaded. So determine the value of the line to line voltage between phase B and phase C at the fault point. Assume that, okay, ABC phase sequence for the alternator. So here we have to find out what we have to find out, the phase voltage of B and phase voltage of C. So line to line voltage means what, VB minus VC basically, right? Pretty simple. So for this we need to use this formula, right? So VB is V0 plus alpha square. So this is the alpha operator, right? 1 at an angle of 120 degrees. So alpha square would be 1 at an angle of 240 degrees. And your VC is this. So V0 is what we know, it is the minus Z0 I0, and V1 is EG uh, minus Z1 I1, and V2 is also this. So you know every value. You just substitute this. So I have just shown it directly here. It comes out to be your 9.382 kilovolt, which is your option number B, I guess. Yeah, B. 7 and 8 were pretty simple problem. I hope these two are clear.
Yeah, yes.
Now, yeah, let's come to question number 9. So this is also pretty simple problem. So a 20 MVA 11 kV alternator with solidly grounded neutral. See, solidly grounded neutral. So your Xn becomes 0. Has a subtransient reactance. Okay, so this is also the same problem. 7, 7, 8, 9. So here it is said that it is intended to limit the fault current for the most severe fault at the alternator terminals to the solid three-phase short circuit current level. So your as we saw that the most severe fault is line to ground fault, right? And they are trying to restrict that current level to the solid line to ground fault limit. So find out the minimum value of the pure reactance to be included in between the neutral of the alternator and the ground for this purpose. So initially we were using a solidly grounded, so there was nothing. Now since they are trying to resist this fault level, so that is why they are connecting a reactant. So basically their equation would be this, right? So your fault current of line to ground fault would be same as that of three phase fault. You know everything, right? So only thing is that you have to so initially in this formula, if we go to question number 7, so this there was no reactance, right, between ground and neutral, so that is why we were using 0. Now there is a Zn, right? Because that is what we are trying to find out, because we are trying to restrict this to this line to ground fault to three phase fault. So this is the formula for three phase fault, right? And you just try to find out. So this comes out to be 0.123 per unit, which I mean, when you find out in ohms, it comes out to be 0.744 ohms, which is your option number A, I guess. So this is not within the limit 0.744, but you can, since this is close, you can choose this option because other options are quite far away, right? So this is option number A, the answer. So these were the connected three problems, 7, 8, and 9. I hope these three, all of these three were clear.
Yeah. Yeah.
Now, last question is question number 11. Um, so this is a 50 hertz, 50 MVA, 13.2 star grounded alternator. This thing is connected to a delta star transformer as shown in figure 10. So this would be 10, right? Not 11. Figure 10. Now here they have mentioned all the positive, negative, and zero sequence impedances of the alternator, and the transformer is this thing, right? Rated at, this is the rating, so this is delta side and this is the star side with solidly grounded star, right? So there is no yes, as you can see, this is solidly grounded. This is the reactance sequence, reactance of positive, negative, and zero sequence reactance of the transformer. Now the line impedance between Q and R. Okay, this transmission line basically is this thing. So here also they have mentioned every these three things, and this is based on the line voltage at 100 MVA base. So this is 100 MVA base. You have to take a note of this. So this is in 100 MVA base. Now find the fault current for a double line to ground fault at this point, right? Basically the fault is occurring at this bus basically. So at this point, what would be the fault current level? So now again here, since we are having a transformer, so our positive and negative sequence reactance would be just the same, right? We have to take every component reactance, positive and negative, we have to connect them in series and find out what is the value. But for negative zero sequence reactance, since this is a delta star, so your configuration would change and you have to draw it separately. So we'll come to that. Now this is the positive sequence reactance diagram. Since this was, so here every component is mentioned. So this is your synchronous generator 0.12. This is your transformer 0.15, and this is your this thing transmission line, right? So 3x1 is 0.12, right? So x1 would be 0.04. But you see this line, this is on a 100 MVA base, but our base that we have considered is 50 MVA. Therefore, this would be what, 0.02, right? Because this transmission line is based on 100 MVA. So as a result, this would change to 0.02. Hence, your when you add these things up, this would be 0.29, and this is also the same for the negative sequence reactance also. Now, when we come to this zero sequence diagram, so you see that this side is delta, right, and this side is star with solid grounded. So as a result, you would have something like this. And again here, as you see, this x0 is j0.12, right, but this is specified at 100 MVA, but our base is 50. So that is why I did the small calculation. So this would be 0.06. So as a result, your x0 would be something like this, j0.21. Now you know the formula, right, for LG fault. So this is the positive sequence current. You find out this. So and then you find out what is the, I mean, using voltage divider formula, you find out what is the zero sequence current. And then, I mean, it is the fault current is 3 times of the zero sequence current, right, for double LG fault. So you just find out this. So you we calculate what is the base current and multiply this with the into 3 I into this base current basically. And also one important thing, this is a transformer, right? So this is 13.2 and 120 kV, and we are trying to find out the fault level at point R. So this is a 120 kV line. So that is why your base voltage here, this was, we were taking the base to be 13.2. Now since this is a HV line, high voltage side, so your base voltage would now change to 120 volt. Therefore, I mean, you can't use 13.2 here. So because this is a HV line, right? So you get to 40.563 ampere. So as a result, your value is this is 1.0165 kilo ampere, which is your option number D. So this was, I hope this problem was clear.
Yeah, yes, it is. Okay.
Yeah. So yeah, this is all. I mean, there is also a question of question 10. So this is pretty simple. I haven't solved it. I I will upload the question paper also, this PDF. You will see the question number 10. Question 10 and question 11 are connected, only that the fault was in question 10, the fault was at point Q. So you can solve that. The process would be same only. So I mean, you can try that. I'll provide the answer in the YouTube video only when I'll post that. You can try that. So this was assignment 11. Pretty simple. I mean, I to find this fault analysis to be the most easiest. I mean, to me at least, I feel that this is one of the easiest as well as the most important topic of power system. And also the upcoming assignment 12, that transient analysis of swings of synchronous generators and motors. That is also another topic. Easy topic, I guess. So yeah. Okay, I'll upload this video and the PDF file of this by today only. So you go through the questions. If you have any problem, you can comment in the video, YouTube video only.
Okay. Okay.
Yeah. Okay then. So we are done for the day. So we'll again meet next week with the last assignment of this course.
Okay.
ठीक है, चलो, bye.